In this section of the course, we are going to talk about properties of real numbers. So the first thing to do when we're talking about properties of real numbers is to discuss what types of real numbers we're going to be looking at. Okay, so we have different sets of numbers that we consider when we look at pre-calculus. The first type are the real numbers. And the real numbers are made up of some different sets. There's the rational numbers, the integers, and the natural numbers that make up the rationals. And then the rationals and the irrationals make up the real numbers. Okay? So to talk about what these sets are, I'm going to start with the natural numbers. It's kind of down here in my list, but of the sets that we're going to talk about, this is the smallest set that we're going to look at. The natural numbers are basically all of our counting numbers. So 1, 2, 3, 4, 5, 6, etc. All of those numbers, when we're counting things off, those would be considered our natural numbers. The integers is a set slightly larger. It includes all of the natural numbers, all of the negatives of the natural numbers, and 0. So one way we would write this and if you notice after each of these sets, there's kind of a symbol after them. So the natural numbers have this symbol. This is how we denote it, this bold-looking N. For the integers, the bold-looking Z is our notation for the set of integers. Rational numbers are all of the numbers that are both natural numbers and integers, but it also includes anything we can write as a fraction, or a terminating or repeating decimal. Okay? So usually you'll see this set written, it's the set of all x such that x is equal to a p over q, where p is an element of the integers and q is an element of the natural numbers. Okay? So anything we can write as a fraction. Again, any fraction where we can take it down and write it as a decimal, it's either going to be a decimal that ends or it's going to be a decimal that repeats. Okay? These sets here, if we look at anything not in this set that we still consider a real number, those are what we consider irrational numbers. These are basically all of the non-repeating, non-terminating decimals. Another way to think of this is it's all of your roots that don't simplify. It's all of your transcendental numbers. Some examples of irrational numbers are things like square root of 3, square root of 5, fourth root of 2. All of those would be irrational numbers. Also things like pi and e. Okay? There are many others. Okay? These two bigger sets, the rationals and irrationals, make up all of our real numbers. Okay? And again, just like our bold notation for naturals and integers, we use this bold R for our real numbers. Okay? Now there's one more set of numbers that we can look at, and that is the complex numbers. But you'll find that for most of what we're going to do in pre-calc and calc, we're not going to talk too much about the complex numbers. Those come back in more advanced calc and more advanced mathematics. But we do a little bit with the complex numbers. And basically these are numbers of the form a plus bi. Okay, the set of all these such that a and b are real numbers and I is the square root of -1. So anything that we can write in that form is considered a complex number. Okay. So there's our different sets of numbers that we're going to work with. And again, the idea is we want to be able to do different properties on those. Those properties are what's going to allow us to do a lot of the mathematics that we're going to see in this course. Okay? So to look at some of the properties, we're going to start with the three main properties of numbers in general. The first is the commutative property. And here, the commutative property basically just tells us order can be changed. Okay? I can commute things, which means to change their order. And it doesn't matter which way it's written, as long as it's the same terms and the same operation, then that works. For the commutative property, this works for two of our operations. We have the one for addition and one for multiplication. Okay? And again, they're both telling us that we can change the order of things. So if A and B are two real numbers, A plus B is going to be the same as B plus A. Likewise, for multiplication, if I'm looking at two real numbers, A and B, A times B is going to be the same as B times A. One thing to make note of is that your commutative property does not work for subtraction or division, and you can check that. So take two real numbers and try and subtract them and see if you get the same thing. Or do it with division. You'll find that you usually do not get the same things for these. Okay? The associative property basically tells me that grouping can be changed. Okay? So if I have three or more real numbers that I am performing operations on, it doesn't matter how I group those together, the result should be the same. Okay? And again, there's one for addition, and there's also one for multiplication. Okay? So for the addition property of associativity, it says that if I take A, B, and C, and I want to add them together by taking A and B first and then adding on C, I'm going to get the same thing as if I take B and C and add those first and then add A to that. Okay? For multiplication, same thing. If I multiply A and B and then multiply by C, I'll get the same thing as if I took B and C and multiplied the result by A. Okay? The last main property is the distributive property. And the distributive property, again, is just what it sounds like. It means that I can distribute multiplication or division over addition or subtraction. Okay? So if, for example, I have some number that I want to multiply by a b plus or minus c, here it doesn't matter if I'm adding or subtracting, it says that I can take that multiplication and apply it to each term inside and then perform the addition or subtraction. Okay? This is what we would consider something that is left distributive, because I'm distributing on the left side of the terms. We also have what we call right distributive, which basically does the same thing. If I have b plus c and I want to multiply by a, again, we can see that I'm going to get the same answer. It doesn't matter what side I'm on, because again, the property of commutativity holds. Okay? And then if we look at division, again, the same thing is true. So if I have a b plus or minus c and I divide by a, here I can distribute this as a b over a plus or minus c over a. And again, here the thing to keep in mind is that these are real numbers. These are not expressions, these are numbers. So if I have numbers I'm adding and subtracting and then dividing by something, I can break it apart like this. And again, the order doesn't matter. If I wanted c plus or minus b, over A. Again, I could do it either way. In addition to our properties of real numbers, our commutative, associative, and distributive property, there are also other properties that relate to just general operations and other things that we'll see with real numbers. Okay. Now, a lot of the terminology I'm using, again, you don't necessarily need to remember all of the terms, but you should know that these properties exist and be able to use them when you're asked to simplify expressions or solve equations. Okay. The next set of properties we're going to talk about are negative properties. And so the first thing I want to mention here is that you should recall that the negative can be used two different ways. Putting a negative in front of a number, we can think of making the number the opposite, or taking a positive 3 and making it a negative 3, or a negative 3 to a positive 3, the opposite of each other. But the negative can also be used as a subtraction. Okay? So when you're looking at these minus signs or negative signs, you have to take it into the right context and determine how it's being used in that situation. In these cases, these are all being used as negatives. So the first property says that if I have a negative number and I put a negative in front of that, here it is being treated as an opposite. And so all it's going to do is cancel out these and make the sign positive. Okay? Now that works both ways. If I put a negative in front of a positive term, obviously it's just going to make the answer negative. If I am multiplying numbers and I have an even number of negative signs, so for example, if I have a negative A times a negative B where there's two negative signs, these negatives cancel out and I'm just looking at the product of the numbers. Okay? So here, this is true for all even number of negative signs. Okay? If I have an odd number of negative signs, 1, 3, 5, 7, 9, etc., so like in this example, a negative A times a B, then here I'm still going to take the product of the two terms, but because there's an odd number of negatives, they don't cancel out, and so I'm just left with a negative. Okay? And again, here this works for any of the odds. So if I had A times negative B, the answer would still be negative AB. My negative can also work like my distributive property. So whether I'm looking at an addition or a subtraction, it does change things just a little bit. And this is one area when we get into simplifying expressions using factoring or rationals, where a lot of people make mistakes. Because in this instance here, if I'm looking at this negative using the distributive property, this is saying minus A minus B, or negative A minus B. In this case, when I distribute that negative, I'm going to see a negative A plus B. Okay? And so notice in one case it's changing the signs on both terms, in the other it's not. And it's again because when I distribute, I'm applying that negative to different types of numbers. Okay? The next set of properties that we're going to look at are properties of sets. And here, this is mostly notation more than it is a property. You're going to see different types of notations throughout this course, and this is the first set of them that you're going to see. These first two symbols we'll use just a little bit. There's a couple instances where we use these and need to know what they mean. They're not as used as some of the other symbols you will see in this course. This first one is what we call a union. Okay, so anytime I see that big U there, that's our union of sets. It means that I'm looking at terms combined from each set. Okay, and here we can give kind of a quick example. Let's say I have the set 1, 2, 3, 4. And then I have a union of the set 2, 4, 6, and 8. then if I look at the combined terms from them, my union is going to be everything that's in that first set plus everything in that second set. And if you'll notice, the terms that are in both, I'm only writing once. I don't need to write them down more than once. So it's everything in here combined with everything in here. Okay? The second one here is what we call the intersection. Okay? And the intersection is basically terms that are in both sets. Okay? So if I use the same set that we had before, 1, 2, 3, and 4, and I want to intersect that with 2, 4, 6, and 8, then I'm only going to pull out the things that are in common in both of them. And as we can see here, 2 is in both of those sets, and 4 is in both of those sets. Okay? So it's where the 2 overlap is another way to think of that. Okay? The union we will use a lot. We will talk about open and closed sets. We'll look at some inequalities, and in both cases you may have to do a union of sets. The intersection is something that is used later on in mathematics. We'll do a little bit of it in this chapter, but you'll mostly use it later on. Okay? These next two symbols are both dealing with interval notation. So if I'm looking at a set on a number line, this is going to tell me where the intervals exist. This first set here is what we call open interval, an open interval. Okay. An example of what this looks like is if I said the set from 1 to 3. It's considered an open interval because it's not going to include the endpoints of that. So if I'm looking on my number line, 0, 1, 2, 3, and 4, I want all of the numbers that are between 1 and 3, but not including 1 and 3. And here, when we say that, you've got to remember from our sets of numbers, there are many rational numbers that fall in between these. Even though I've made the tick marks at the 1, 2, 3, and 4, there are many numbers that are between those. So to define this set, what we're going to do is we're going to say it's starting here at 0. It's not including it, so I'm not going to use that as a point. And it's going to end here at 3. Same thing, it's going to be an open circle because I'm not including that. But then it's going to be everything in between them. Okay? A closed interval is very similar. The only difference is how your endpoints look. Okay? So an example here would be, let's say I'm looking at that same group of numbers, but now I want a closed interval from 1 to 3. Okay? So same thing if I go to my number line. I'm going to have a point at 1, but again now I'm including it. So I'm going to close that circle in. Same thing at 3, I'm including that, so I'm going to close that circle in. And I want all the points in between there. Okay. And again, we can have combinations of these. So we could have a half closed or a half open interval. Okay, so for example, if I had something like 2 to 4, where 2 is not included, but 4 is, we can see here, for the 2, because I'm not including it, I want to have an open circle. For the 4, because it's included, I'm going to color that in. And then, again, it's going to be everything between them. Okay. Now these symbols are very similar to our open and closed interval. The only difference is it's a different notation. These are what we call inequality notation. These again are what we call our interval notation. Okay, so here, this first one is what we call open inequalities or non-inclusive inequalities. Okay, and it works just like this. So if I said that x is less than 3 or x is greater than 2, okay, on our number line, again, if this is 3 or this is 2, less than 3 just means I'm looking there and everything below it, just not including 3. And for greater than 2, I'm looking there, but everything above it. Okay, and likewise for this one, we have what we call inclusive or closed inequalities. Okay, and so again, we've got the less than or equal to or greater than or equal to. If I'm looking at x less than or equal to 2 or x greater than or equal to 3, again, I'm just going to put those on my number line. Again, the difference being instead of open circles, I'm going to include those points. So here, x being less than or equal to 2 just means I'm looking at everything below 2 up to and including it. X greater than or equal to 3 is everything bigger than 3, but again, down to and including 3. All right, our next set of properties are our properties for fractions. And these are ways we're going to be simplifying fractional expressions. Okay? For many of these apply to the different operations that we can do on fractions. And again, most of them behave similarly, but not all of them. Okay? For the first one, this is what we consider the multiplication property. And the nice thing here is if I have a over b times c over d, this is just going to be ac over bb. It does not matter what the fractions look like. If I'm multiplying, I can just multiply the tops or the numerators, multiply the bottoms or denominators. Okay? If I am dividing, so this is our division property. So a over b divided by c over d, it says the first thing I'm going to do is rewrite it as a multiplication so that AB over BC is my solution. Okay. Now for addition and subtraction, we have two separate properties. And it depends on what your expressions look like to determine which way you're going to which property you're going to use. The first is if my fractions have the same denominator, or if they can be reduced to have the same denominator. Then the addition or subtraction is simply working with the numerators. And that just means I'm going to take and undistribute that division. It doesn't quite look like a distributive here, but if you remember that last distributive property, it said if I divide by c, I can distribute it over a sum or difference. Division of fractions, addition or subtraction of fractions with like denominators is undoing that distributive property. So this is just saying I'm going to take a plus or minus b and then divide it by c. Okay, so I'll combine those tops first and then divide out. Okay, so this is again if I have the same denominator. If I don't have a same denominator, then what we're going to do is use your LCD, which you may or may not remember. LCD stands for least common denominator. Okay. The long way to get that LCD is what we'll do here, and that's just, I'm going to multiply by the other denominators. So in this case, I'm going to multiply by D. Here I'm going to multiply by B. And put it over that common denominator. Okay. The least comes in because some of your numbers you can simplify. And so if I've got two numbers and I want it to be my least common multiple of those, I'm going to find the smallest number that I can make out of both of them and then multiply by that missing term. Okay. In general, we can do it this way and then reduce. Okay. And that's what this next property is talking about. This is our reduction property. It says that if I have a fraction where the top and the bottom can be rewritten as products of terms where part of those products are the same factor, then I can remove that factor. Okay? So this is basically saying I can take A times C over B times C and rewrite it this way, right? Because that's what our product property says. And then from here, notice C over C is just 1. So I'm just going to get A over B. Okay. And then our last property, this is our cross multiplication property. And this one I hesitate to put up because this is one that a lot of students confuse with the multiplication property. These are very different properties, and the main difference is, in this case, I'm actually looking at a proportion. If I have two fractions that are equivalent, then I can use the cross multiplication property. This one is for multiplying. If I'm multiplying, I'm going to go straight across. But if I'm cross multiplying, where I'm looking at a proportion, then it says A over B equal to C over D. I'm going to take and cross multiply those products to get that AD equals BC. The last set of properties that we're going to look at are properties for absolute values. And before we can get into that, I want to define what the absolute value is. And there's two ways you can define the absolute value. Okay? The first is what we call this kind of numeric representation of an absolute value. And that says that the absolute value of A is a real number A if A is greater than or equal to 0, but it's the real number negative A if A is less than 0. Okay, so for example, if I'm looking at the absolute value of 3, this is just going to be 3 because it's bigger than 0, so it's just the value of the number. If I'm looking at the absolute value of negative 5, well, negative 5 is less than 0, so we're going to take the negative of negative 5, which is just 5. Okay. The other way to think of it is using our distance. Okay, so what this is saying is if I have some points on a number line, I'm just going to call them A and B, then our distance from A to B is B minus A in the absolute value. Okay. And the reason we put it in the absolute value is because here it doesn't necessarily say that A is less than B. Our picture could look like this. And so again, our distance between A and B should be the same thing. But in order for that to be the same thing, I need those to be absolute values. Okay? So there's another property. Okay? If I have a subtraction of two numbers inside of the absolute value, that difference is equivalent no matter which order I am looking at. Okay? So if you remember, our commutative property did not hold for subtraction, but if I put absolute values in there, it does hold. Okay? Some of the other properties that we're going to see for absolute values, this first one is actually more of kind of something just to be stated. It goes along with our definition of absolute values, And that is, it doesn't matter what number I put in there, when I take the absolute value of it, it is always going to be positive, meaning greater than or equal to 0. And we can kind of see that here. Okay? The absolute value of a negative number and its opposite positive number is always going to be exactly the same. Okay? So if I take the absolute value of A and the absolute value of negative A, I am always going to get the same thing. And again, we can see that from our definition there. If I take the absolute value of 2 and the absolute value of negative 2, both of these are going to come out to be 2. Okay. For multiplication and division, our absolute value is distributive, meaning if I have a product inside of an absolute value, I can take the product of the absolute values. Okay? So for example, if I look at the absolute value of 6, I can say this is the absolute value of 2 times 3, which is the absolute value of 2 times the absolute value of 3. And evaluating both of these, you can see that that's true. Okay? Same thing with division. If I have something being divided inside of the absolute value, I can separate that to a top and a bottom, take the absolute value of each, and that'll give me my simplified answer. Okay? And again, an example would be if I had 8 over 2, I can make this the absolute value of 8 over the absolute value of 2, which is 8 over 2, or 4. And again, we can see here, dividing would give us absolute value of 4, which is 4. Okay, so that's all of the properties you're going to see in this first section. This was just a quick review of some of those that you're going to deal with in this class. We will look at some other properties later on, but you should know these. Again, if you don't remember the names to all of these, that's okay. And you may not even remember that you can use some of these. But being aware that they're there will make simplifying some of your expressions later on a whole lot easier.